All right, so now we want to talk about radioactivity, which you've probably heard about, radioactivity. So what is radioactivity? It's a spontaneous, it's a random decay of the nucleus. Okay? So the nucleus becomes unstable, and in order to become stable, it has to emit something, get rid of some energy. Okay? But it's random, it's spontaneous. Okay, let me get more of this random. Let's say I had a whole bunch of radioactive nuclei right here. Because it's random, I am completely unable to say which nucleus is going to decay. All right? I can't. However, but I can say how many nuclei will decay in a certain amount of time. I can't predict which ones though, but I can say how many will decay in a certain amount of time. Okay, so it's probability again. Are you surprised? You shouldn't be surprised, right? Quantum mechanics is probabilistic. Okay, so radioactivity, it means energy is released. So you just kind of imagine, somebody really, really hyper, unstable nucleus, and the only way they're going to become stable is to get rid of some energy, right? Okay, so there you go. All right, so basically what we're saying is for radioactivity, you have an unstable, high-energy nucleus, gets rid of some energy, becomes a low-energy, happy, stable nucleus. Okay, it's a type of ionizing radiation. That means it ionizes atoms. That means it breaks molecular bonds. Remember, we're talking about 1 million electron volts of energy, okay? And so it's dangerous, all right? It's dangerous to us. And we'll talk about that, all right? Okay, and remember, microwave light, microwave energies, ultraviolet energies, these are all like, electron volts. They don't really do anything, right? But we're talking about millions of electron volts, all right? So you got to be careful. Okay, now there's going to be a lot of math. Not a lot, but. Okay, so again, we're talking about unstable nuclei, right? So we have a bunch of stable nuclei, and they're going to decay, okay? So this is this famous exponential decay. So you see this kind of equation all over the place in science, not just physics. So you have a certain number of nuclei, right? And so the number of nuclei depends on the time, right? So this is like n as a function of time, right? So the number that you have, n of t, so n as a function of time depends on how many you had initially, times e to the minus rt. Okay, now hold on. Okay, whenever you have a graph, y equals e to the minus x, it looks like this. All right, so it's called a decay curve, e to the minus x. So what we're saying is that the number of nuclei that you have at any specific time equals the number that you had initially times e to the minus rt. Now r, what's r? It's called the decay constant. So every isotope has a unique decay constant. Now, some people don't like this equation. So what they say that the decay constant equals 1 over the time constant. So this is a tau, right? Remember the Greek letter tau? So this is called a time constant. And then they say, okay, so the number of radioactive nuclei at any particular time equals the time you start, the number you start with times e to the minus t over tau. And that's actually nicer because then you can make a nice plot. So let's just say for some element, every isotope has a unique tau. So let's say, after one tau, so however many seconds. Okay? Well, after 1 tau, so you have n, you have n equals n0 e to the minus, remember, the t is tau, so you have minus tau over tau, which is n0 e to the minus 1. All right, well, if you deal with this kind of stuff a lot, you know that e to the minus 1 is 0.37, right? So here it is. So here's how much you start off with. So this is the number of nuclei remaining. This is time. After 1 tau, you have 0.37, right? 0.37. Okay? After 2 taus, after 2, you get this. You get n equals n0 e to the minus. Now the time is 2 tau. 2 tau over tau, which is n0 e to the minus 2. Well, e to the minus 2 is 0.13. So that's right there. All I'm saying is that, people that do this stuff, they know what e to the minus 1, e to the minus 2, e to the minus 3. And so if you just put the time in terms of tau, then it's just easy to plot them, all right? It's just mathematically easy to do. So, okay, so you see this sometimes, you see that sometimes. Now let me tell you the truth. I mean, this is true. I haven't lied, but in the real world, like if you go to a nuclear medicine department in a hospital or something like that, they're not going to talk about taus and r's. They're not going to talk about the decay constant and the time constant. They're not going to talk about that. They're going to talk about half-life. All right, half-life. So what they're going to talk about, they're going to use this equation. So the number of radioactive nuclei remaining, so you all start off with n0. So the number remaining, which is n, if you want, okay, you can put a little t there if you want. I'm just trying to show you that this means that n depends on time, okay? Sometimes people don't bother with the n, with the time, whatever, doesn't matter. But n depends on time. So the better way to write it is this. The number that remain at some time equals the time you start off with times a half to there's a t and there's a t half. Okay, what in the world is that, all right? So t half is called a half-life. Half-life. All right, now what's a half-life? Okay, and the thing is, every isotope has a unique half-life. And people in nuclear medicine, they usually know, because they use it all the time, the half-life of most of the isotopes that they use in their department, So what's a half-life? Okay, so let's just say that this square represents a number of radioactive nuclei. All right? Okay, whatever. All right, so after one half-life, half of these will have decayed. Now, I can't tell you which ones, because it's a random process, right? Probability. But all I know is after one half-life, half will have decayed. All right? So I have half what I used to have. After another, in other words, after 2 half-lives, half of these will have decayed. After another half-life, half of these will have decayed. And so forth and so on. So that's just, this is what people use in the real world, right? Because you just remember the half-lives, and it's just easy, right? After one half-life, half. After 2, a fourth. After 3, an eighth. After another, 16th. It's just bing, 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 bing. Okay, so let's talk about that. All right, so this is great. So here we have 16, right? And this is ridiculous because you have, huge numbers, but this is just to make the drawing easier. So let's say we have 16 radioactive nuclei. So that's n0 at time equals 0, okay? And this is the time axis, but we're just going to talk about half-lives. So after one half-life, half of those guys will have decayed. So they're going to become something else. So after one half-life, instead of having 16 reds, we should have 8 reds. 1, 2, 3, 4, 5, 6, 7, 8. And the greens are what the reds became. Okay? So what we're saying is that when we have a red, when it decays, it becomes green. All right, great. So now we have 8 reds and 8 greens. After another, so here we are, right? 1/2 of n0. After one half-life, we have half as many as we had at the start. After a second half-life, well, we had 8. Now half of those are going to go away. So what's half of 8? 4. So now we have 1, 2, 3, 4. And the rest are all greens. So we're down here, a fourth. After a third half-life, what's a half to the third power? It's an 8. So we have an 1/8. So we had 4 reds, now we have a half at 4, which is 2. Ta-da! All right? So it's just easy, It's just a half. So you say a half to the first power, second power, third power, fourth power. It's easy. People like it. So here's another way to look at it. So this is fraction remaining, and this is years. So this is carbon-14. So carbon-14 has a half. All right, so this is years, and this is half-life, right? See, it says years here, and then it says number of half-lives. All right, so fraction remaining. So at time equals 0, we have 100%, 1, right? The fraction is 1. We have all carbon-12. Okay, after one half-life, 6,000 years, we have, what's the fraction? Half, no kidding. After a second half-life, we have half of a half, or a fourth. We have a fourth, After 3 half-lives, we have an 1/8. After 4 half-lives, we have a 16th. After 5 half-lives, we have a 32nd, right? 2 to the 5th is 32. Okay, so you can just make this decay curve. Isn't it great? Half-lives are great. Okay, so there it is. The number remaining at some time t equals the number that we have initially times 1/2 time divided by half-life. Okay, awesome. Now, here's another way to do it if you really want to. Okay, this is just math. I'm not going to prove it. You can do it. This is exactly the same thing as this. This just uses natural logs and exponentials, but they're equivalent. So, whatever you want, this one or this one, they're exactly the same thing. So just have 2 ways of doing the same thing, Okay, now this is what I want to, So look I said that every isotope has a unique half-life. I mean, look at these things. So carbon-14, I just told you, has a half-life of 6,000 years. That's a long time, right? Or look at plutonium-239, 24,000 years. Look at uranium-238, 4.5 billion years. Uranium-235, 0.7 billion years. I mean, that's important, right? I mean, that's really important. Why is it important? Well, think about it. Nuclear power plants produce radioactive waste, the uranium. And so what are you going to do with the radioactive waste? You got to store it somewhere, right? Well, it's incredibly dangerous. So you got to store it somewhere safe. Well, I mean, you got to do it safely. Well, what do you want to do? Do you want to store it at every nuclear power plant? And so you have the possibility that you have all this incredibly dangerous stuff scattered all over the country, or do you want to have it at one place where it's super secure, you have guards, I mean, it's super, super secure. What do you want to do? Well, years ago, the government decided that they wanted to have it, rather than having it spread all over the country, they wanted it at one place, in Yucca Mountain in Nevada. Well, how would you feel if you're the people in Nevada? Look, this stuff has a half-life of 1 billion years. Billion years! So what if it's not so safe? You think it's safe, but it's not. Well, how do you feel? It's not going to go away. It's not going to go away, right? After 1 billion years, half as much is left. Well, it's so incredibly dangerous. And so this is really, really important as far as like nuclear waste and stuff like that. And in medicine, we'll get into it. Okay, so that's what people deal with in nuclear medicine facilities and so forth, half-lives. Now, let's say, here's something else that people deal with. So like if you're disposing of nuclear medicine, like as a doctor or nuke med tech or a pharmacist, half-lives, right? Well, how about if you're, doing a survey, somebody spilled some radioactive material and you got to survey it with a Geiger counter or something like that. Well, then what you're really doing is you're measuring decay rates. You're measuring decay rates. So let's talk about that. So the decay rate, uppercase R, which is just D, that's right, this is 221. dN dt, right? That's how quickly the radioactive materials decay, all right? And I'm skipping a whole bunch of math, all right, skipping a lot of math. And so you have R0, right, the decay rate initially times our good old friend, 1/2 to the t over half-life, okay? And again, if you want to be fancy, you can say R0 e to the minus ln 2 over half-life times t. But this is easier, you know? But that's okay, whatever. All right? Now, what are the units for this? Well, this is the decay. This is the time. So it's called a becquerel, after the guy that figured it, you know, learned about radioactivity. So it's decays, decay per second is a becquerel. So that's the metric system unit for decay rate, right? There's a delta, there's a dt, so it's a rate, all right? Rate. All right, let's, oh yeah, now, if you go to a nuke med department in a hospital and you have older people working there, and you say, how many becquerel, what's the decay rate in becquerels, they're going to look at you like you're weird or something, because a long time ago, people didn't use becquerels very often. They used what's called a curie. And a curie, right now we know that a curie is 3.7 times 10 to the 10th becquerel. So a lot of the older people use curies. The newer people were trained to use becquerel, so whatever. But becquerel is the metric system unit. But like I said, curies are still used a lot. Let's do an example. Finally. Okay. So, Tech 99, technetium-99m. So Tech 99 is a very commonly used radioactive drug in nuke med. So Tech 99m has a half-life of 6 hours. A common dose for diagnostic nuclear medicine scan is 20 millicuries. See, old, right? 20 millicuries. How much of this dose in curies and in becquerels remains after 24 hours? Okay? So here's the easiest way to do this. The easiest way to do it is in half-lives. Okay, half-lives. All right, so Tech has a half-life of 6 hours. So half-life is 6 hours. Now, what we want to know is how much is left after 24 hours. Well, what's 24 hours? 24 hours equals 4 half-lives. Okay, that's what you always want to identify. How many half-lives? All right, so we start off, right? We start off with 20 millicuries. We start off with 20 millicuries, and then we see how much is left 4 half-lives later. So we have a half, and then the time is 4 half-lives. Well, so the time, so this t is 4 half-lives. So we have 4 half-lives divided by 1 half-life is 4. Okay, so it's 4. Isn't that awesome? Well, fancy math, you know. So that's just 20 millicuries. And let's see. And what's a half to the 4th? A 16th, right? And so we get 1.25 millicurie. Okay. Now, if we want to convert that to becquerels, we can do it. It's just a conversion factor, not a big deal. So 1.25 millicuries. All right, so, okay, so what's a millicurie times 10 to the minus 3, right? So we have 0.00125 curies. And then conversion factor, 3.7 times 10 to the 10th becquerel per curie. And that equals 4.63 times 10 to the 7th becquerel. You see why people like curies? You know, you don't have these crazy, 20 millicuries, that's nice, right? Nice, easy number. 4.63 times 10 to the 7th, what's that, you know? But anyway, whatever, okay. All right. So this is incredibly important. Let's say you're a patient and you have an appointment for a scan, a nuke med scan, and you're supposed to be there at 8 o'clock in the morning. So what that means is that the doctor, will have contacted a nuclear pharmacist and said, I need 20 millicuries of Ch at 8 o'clock in the morning. Now, so typically the nuclear pharmacists, they work at night or in the morning, like midnight to 8 a.m. or something like that, make a lot of money. But anyway, so when they deliver the Ch to the hospital, let's say they deliver it at 7 o'clock, it's not going to be 20 millicuries, it's going to be more than 20 millicuries, right? Because the doctor wants it 20 millicuries at 8 o'clock. Okay, so if the patient is late, that's bad news because the doc wanted to scan with 20 millicuries. If you come 2 hours late, it's decayed, right? I mean, it only has a half-life of 6 hours, And so that's why the nuke med techs get really ticked off when people are late because there's less material, so the quality of the scan has decreased. And if you're really late, they just say, forget it, come tomorrow or something like that. So there you go. Okay, 3 main types of radioactivity. 3 main types of radioactivity. Okay, remember we talked about an alpha? I said it was like a bullet. So what's an alpha? An alpha particle, okay, so there's 3 main types. First one is an alpha, right? And all it is a helium-4 nucleus. That's all it is, right? So, I mean, don't take this, proton, neutron, proton, neutron. That's what it is, right? That's the nucleus of a helium-4. Just 2 protons and two neutrons, okay? By the way, you can write helium-4 nucleus like that, or some people write it like this. You can put helium-4. Some people write it like this, helium-4. Some people write it like that. I mean, you don't really need to do this, but this is really the best way, because then if you write it like that, you don't have to keep looking at your periodic table, right? This is the number of protons. That's the number of protons and neutrons. So this is really the best way, so you don't have to keep looking at the periodic table to figure out how many protons you have. Okay? So write it like that, write it like that, write it like that, whatever you like. I mean, if it's helium, you know it has 2 protons, but what if you don't know that? Just write it down, then you know it. Whatever, 6 or half a dozen, okay? So the first type of radioactivity is a helium nucleus. So these alpha particles that Rutherford used were helium nuclei, little bullets. Okay, the second type of radioactivity is called beta, right? That's a beta, and that's an electron or a positron. A positron is just a positive electron, right? It's the antiparticle of an electron. It's nothing mysterious. It's not a big deal. It's just like an electron, but it's positive, right? Positron, right? Positron, okay? The third type of radioactivity is called gamma. Okay, gamma is just a high-energy photon. High-energy photon. All right. So those are the 3 main types of radioactivity. Now, think about it. Photons have no mass. They travel at the speed of light. An electron has a tiny mass. Helium-4 has a gigantic mass compared to an electron, right? And so these are very, very different, right? This is positive. This could be positive or negative. This is neutral. So they're very, very different. And to protect yourself, it's going to take different strategies. So let's talk about that. So let's talk about penetrating ability. Okay, why do you care about that? Well, if you ever use this stuff, you care. Like if you're doing some kind of an experiment and you have gammas or betas or alphas, I mean, you got to protect yourself. It's going to take a very different type of material to protect you. So this is the penetrating ability. So look, alphas are stopped by paper, okay? So if there's an alpha source there, it's not going to go through your skin, not a big deal. The problem is if they're in the air and you breathe an alpha emitter, it's going to go into the little tiny, whatever they're called, in your lungs. They're just going to sit there and irradiate you, and that's bad news. Okay, so betas and gammas go right through the paper. Okay, betas are stopped by aluminum. Okay, that's all right. So you can use aluminum shielding to protect yourself. Gammas are stopped by thick lead. So if you've ever gone to a hospital where they do gamma surgery, you know, like for brain tumors or for whatever, you know, cancer, stuff like that, the room where they do it is lined with thick lead, all right, because, you know, you don't want to hurt the people outside, right? Okay. Here's another thing. So let's say we have a magnet. Remember, magnets, well, maybe you don't know this because you haven't had 220. Some of you haven't had 220, but magnets change the direction of charged particles, okay? And so here's a gamma. Well, of course, a gamma is neutral, so the magnet does nothing. Okay, the beta, remember, beta is just a little tiny, you know, low-mass electron, so it changes the direction big time. The alpha is like a Mack truck compared to a beta, so it still changes the direction, but not so much. Now, this is, when we say beta here, we mean a negative electron. Here's alpha is positive, so you can see that it's opposite direction, right? Because this is negative, this is positive. So that's just an example of F equals ma, right? You know? So the low mass means it's going to have a big acceleration, a higher mass, not so much. And here there's no charge, so there's no force. Okay, now we've got to get into, well, let's see, we don't have time. All right, so we're going to get, the next time we meet, we'll get into the gory details of the alpha decay, the beta decay, and the gamma decay. And it's incredibly interesting. Trust me, it's really very interesting, the details. And then we'll also talk about tunneling, and then we'll talk about health, believe it or not, protecting yourself from radioactive decay. All right, thank you very much.